So today we are going to talk about an introduction to amplifier circuits. Away menu. There we go. So let's say that we have the following input waveform. As a function of time. I'm going to attempt to draw just a simple sinusoid here. So we have some signal like so, and this signal in green could represent a voltage as a function of time, current as a function of time, or power as a function of time. And our goal is to make this input signal larger, such that our output might look something like this. Where this curve in red also could be a voltage, current, or power waveform. Well, there are two distinctly different ways to accomplish something like this. We can either use an amplifier, and we'll talk about what that entails over here on the left, or we could use a transformer. And I misspelled it. And we'll talk about what that entails over here on the right. Okay. So the biggest difference between an amplifier and a transformer is that one is an active device and the other is a passive device. Okay. So amplifiers are active devices, which means that they require external power. So some amount of signal processing goes on that requires some external power in order to boost the level of our input signal. Whereas a transformer is a passive device which means that no external power is required. So the largest consequence of amplifiers being active devices or externally powered devices is that the output power does not have to equal the input power, right? So, and what I mean by that specifically is that the signal power at the input can be less than the signal power at the output. Whereas for a passive device, we will find that our output power is always going to be less than or equal to our input power. In an ideal case, our output power for a transformer would be equal to our input power, but because of things like resistive losses, friction and windage losses, and things like that, we'll usually find that our transformers are only able to operate at somewhere in the ballpark of 95% efficiency, depending on their construction and a few other factors. Okay. So for the purposes of this class, we are going to focus on amplifiers, okay? And then when we get to circuits 3 in the fall, that's when we're going to go into greater detail on the behavior of transformers, okay? So limiting our focus to amplifiers, let's really define what an amplifier is, okay? So an amplifier is an electrical circuit or device which we're going to say increases the magnitude. Doesn't have to increase though. Of the signal applied at its input. So I'm going to draw what I'm going to call a black box amplifier here. And on the left set of terminals is where we are going to apply our input signal, which I will simply call X of t, where X of t could represent a voltage, current, or power waveform. And on the right-hand side will be our output, Y of t, which could also be a current, voltage, or power waveform. And the goal of the amplifier is to shape our input signal X of t to give us our output signal Y of t. So we're going to have this relationship. Y of t will be equal to A times X of t, where A is commonly referred to as the gain of the amplifier. So inside my amplifier block, I'll define my gain as the ratio of the output signal to the input signal. And so from this, we can actually classify several different types of amplifier. Okay. So I'm going to make a little table here. I'm going to put the input quantity on the left, the output quantity here in the middle, and the amplifier type over here on the right. And so if our input quantity is a voltage and our output quantity is also a voltage, we have, unsurprisingly, a voltage amplifier. And this is the type of amplifier that we're going to spend most of our time talking about in this class, but in later classes, we'll talk about all of the others in depth as well. On the other side of the spectrum, we could have a current signal as our input, a current signal as our output, and this means that we have a current amplifier. We could also have a voltage signal at our input, a current signal measured at our output, and these cases are called transconductance amplifiers. We could have the opposite, where we have current at our input and a voltage at our output, which gives us a transimpedance amplifier, or commonly a transresistance amplifier. And then lastly, we have power at our input, power at the output. We have a power amplifier. So it may not be obvious to you all, but we actually deal with multiple types of these amplifiers literally every single day, right? For those of us who drive to work and listen to the radio, the reason that we are able to hear anything is because a power amplifier is used to drive the loudspeakers in our car. Another amplifier that's used in our radios is a voltage amplifier. Depending on whether or not you've had your field theory class yet, you may or may not know that signals attenuate or decrease in intensity the farther away you are from their source when they propagate through air. So I usually listen to a radio station out of Shreveport on my way into work, driving to Ruston. And so the closer and closer I get to Ruston, the signal strength is smaller and smaller and smaller. And so a voltage amplifier is needed to increase the signal strength received by the antenna to be processed by the filter circuits and all of that kind of stuff, and then converted into sound that I can hear by that power amplifier. We all have voltage, current, and transconductance and transimpedance amplifiers in our cell phones. They all form the parts of radios and analog signal processing circuitry, okay? So amplifiers are in use literally all around us, right? So what we are going to do over the next few minutes is develop a simplified model for a voltage amplifier circuit, okay? Our ultimate goal here is to apply this model to simplify the analysis required to understand how an operational amplifier processes an input signal. So to really understand why we need a mathematical model to use, I'm going to show you what the internal circuitry of an op amp looks like. Here, yeah. So what I've pulled up here is the data sheet for a MUA 741 general purpose op amp from Texas Instruments. This particular op amp was invented, if you will, in the early 1960s, I believe. It is one of the most commonly used op amp circuits in existence. It's used in lots of simple signal processing circuitry for things like guitar effects pedals, simple radios and things like that. A lot of consumer electronics. And I'm going to scroll down here, continuing to scroll down, continuing to scroll down until we find our functional block diagram for the circuit. Okay. So this is a simplified representation of what the internal circuitry of the MU-A741 op amp is. And the MU-A741, as I said a moment ago, is a general purpose op amp designed very early on after the concept of integrated circuits was introduced. And so this is one of the least complex amplifiers that are in use today. And if we look at this thing, I would argue that it's actually pretty darn complex, right? We have 2 input pins, 2 offset pins, a power supply pin for the positive side, a power supply pin for the negative side, and then a single output pin. So this is what's called a single-ended differential amplifier. It's a differential amplifier because it has 2 inputs, and it's a single-ended because it has a single output. We can see down at the bottom of the screen that the component count for this simplified representation of the internal workings of the op amp contains 22 transistors, 11 resistors, a diode, and a capacitor. So it is pretty darn complicated. And if we were trying to analyze circuits using this model, it would literally take forever. So instead of using this behemoth of a model, we are going to use Thevenin and Norton equivalent circuits to develop a simplified representation that will actually work for practically any amplifier circuit we are ever going to deal with as electrical engineers. Okay. So I'm going to start with another black box, right? So let's consider a simple voltage amplifier circuit. On the left-hand side will be my source. So I'm going to say that I have some time varying signal that's generated by my source. And just for the sake of argument, let's utilize a practical voltage source, meaning that our ideal source will be in series with some resistor RS, like so. And so this is the source side of my circuit. Here in the middle will be my amplifier. For now, we're going to treat it as a black box. And then over on the right, the output of our amplifier is connected to some load that we are trying to drive. And I'm going to consider this load to be simply a resistor for right now, which might be representative of a speaker. So this is the input terminals of my amplifier. So this is where the amplifier's input voltage will be applied. Over here are the output terminals of my amplifier. So this is where the output voltage of my amplifier is measured. And then I'm going to specify here that the voltage drop across my load is VL of T. And I've effectively broken this simple amplifier circuit down into three discrete parts, right? We have our source, which is used to generate the signal that our amplifier takes in. Our amplifier then processes this input signal to create the output signal. And then the output signal drives our load, in this case, RL, and we have some measured system output VL that we can look at. The ideal behavior of this circuit is that our voltage VL of T will be a scaled version of our source signal Vs of T, right? So ideally, we want the amplifier to apply some amount of gain to the input signal, send all of that to the output signal so that our load is driven in the most efficient way, okay? We are now going to develop a model that will replace this black box amplifier in the middle by using Thevenin equivalent circuits, right? So if I were to look in to this system at the amplifier's input terminals, so if I disconnected the source and looked in, what would I expect to see? Well, I will see some resistance Rn. So redrawing some things here really quickly. Here's my source. Here's RS. Here are my terminals. This is where my input voltage is being applied to my amplifier. And then over here, my load isn't going to change at all. So these represent the output terminals of my amplifier. The load connected to the output of my amplifier. And that voltage VL of T. And according to Thevenin's theorem, if I look in to the input terminals of my amplifier, I will see some input resistance Rn. Okay. Now, what would happen if I disconnected my load and looked into the terminals left behind, right? Well, I am going to make an educated guess here and say that I'm going to see a practical voltage source. I could also see a practical current source, but because we're dealing with a voltage amplifier, I'm going to say that it's going to look like a practical voltage source, right? So I should expect to see some resistance, but I'm also going to see a voltage source because my voltage source Vs of T is connected, right? So overall, what I'm going to see is a practical voltage source. And I'm going to call this resistance R out. And I am going to choose to represent this voltage source as part of our Thevenin equivalent as a dependent source. And the reason that I'm choosing to represent this as a dependent source is because I know that I want my output voltage to be a scaled version of my input voltage. So this bit right here is what we are going to call the practical no. Sorry. Amplifier model. And this is what we're going to use in place of a complicated circuit like the one shown here. Right. So there are three critical parts of this practical amplifier model. Okay. They are the input resistance, the output resistance, and our gain. If we know those three pieces of information, we can represent any amplifier using this practical amplifier model. And as it turns out, those are three pieces of information that are very commonly given to us on an amplifier's data sheet. One of the reasons why they're there is so that we can use a model like this to determine how our circuit's going to behave without having to mess around too much with the actual circuitry of the amplifier. Okay. So now let's talk about op amps. So an operational amplifier is a differential voltage amplifier, meaning that it takes in two input signals, right? So the schematic representation of an op amp that we used in circuits one, I'm going to redraw it here. We had a triangle, which is the generic symbol for an amplifier. We had a non-inverting input terminal. We had an inverting input terminal. And we had our output terminal. So I'm going to call this V plus for my non-inverting input, V minus for my inverting input, V out for my output voltage. And then there are also some other pins. We didn't really deal with them in circuits one a lot, but we're going to deal with some of them here in circuits two. So I'm going to go ahead and label them. So I'm going to have a power supply pin. I'm going to call this VCC plus. This is where positive power, positive external power is connected to the amplifier. I'm going to have a negative supply pin, VCC minus. This is where the negative voltage is applied. And then I'm also going to put in these two pins in pink will be optional. We are not going to ever see them, but they do serve a purpose in practical op amps. This is going to be OS plus for offset plus and OS minus for the offset minus. So if we look at our UA 741, this is our non-inverting input pin, our inverting input pin, our output pin. Then we have our positive supply pin, our negative supply pin. And here's our offset null 1 and offset null 2. Let's talk very briefly about the offset null pins and effectively explain why we're going to ignore them in this class, but why we don't ignore them for practical circuits. So the offset null pins are used to correct manufacturing errors. So effectively, the integrated circuit process that is used to develop op amps is very, very good. However, small problems due to the misalignment of various mask layers and things like that can cause an operational amplifier to have a very small output voltage on the order of micro to millivolts, even when the non-inverting input terminal and inverting input terminal are shorted to ground. So effectively, you can see an incredibly small output voltage even when no input voltage is applied. The offset null pins are used to get rid of this offset at the output voltage and fix it to be at true zero or as close to zero as you can possibly get it. For the intents and purposes of this class, we are going to assume that our op amp circuits are perfect, effectively meaning that there is going to be no offset output voltage that we need to fix, which is why we're going to ignore the offset pins in our analysis. So this is the representation of our operational amplifier. What we are going to do is apply our practical op amp model, or excuse me, our practical model to this, so that we can have a tool by which to do circuit analysis. Okay, so this is what our model is going to look like for an op amp. We're going to have our input resistance. Here's Rn. And then the nodal voltage here will be V plus. So this terminal at the top left is what I'm calling my non-inverting input terminal. And this pin here will be then V minus. So that is my inverting input terminal. And I'm going to define the potential difference across my input resistance to be VD, my differential input voltage. Okay, so this is how we're taking into account that we have two inputs. Because we have a differential amplifier, we are actually going to amplify this differential voltage. So the practical voltage source side of our model is going to look like this. We are going to have our gain A, but I'm going to give it a special name, AVOL. This stands for the open loop voltage gain. So the V, anytime we have A with a subscript V, that means we're dealing with a voltage gain. And the subscripts O and L mean that we have an open loop configuration, which means we are not applying any feedback. And I'll get into that more here in a little bit. This open loop voltage gain is what scales our differential input voltage. Here is our output resistance for our practical model. These are our output terminals, V out, and we always choose to have the negative polarity terminal of our output voltage set at ground. So this serves as the reference for our circuit, and I am going to go ahead and extend this ground rail out to the left as well, so that it serves as the reference for our non-inverting and inverting input voltages. Okay. So this thing that I've drawn over here on the right is commonly referred to as the practical op-amp model. And it is what we are going to use to analyze open loop op-amp circuits, positive feedback op-amp circuits, and we're going to begin with this model to analyze negative feedback op-amp circuits until I can show you where the ideal amplifier relationships come from, which will allow us to go back to using what we learned in circuits 1. Okay, so this is our practical op-amp model, and it's what we are going to be using. Now, it does have some limitations, and I'd like to show you what those are. So what I'm going to do here, once my screen updates correctly, there we go. I'm going to draw a little circuit, and we are going to analyze it using the practical op-amp model. So this is going to be a fairly simple circuit. Here we have our op-amp. And these top and bottom terminals are going to be for our power supply. So let's say that we apply a 1-volt signal to our non-inverting input terminal. We ground our inverting input terminal. We apply 10 volts DC at our positive power supply terminal, negative 10 volts DC at our negative power supply terminal. One thing that I do want to point out here, there's nothing that's requiring us to have the same amount of positive voltage as negative voltage on our power supply. We could do 10 volts on the positive supply and negative 3 volts on the negative supply if we so chose. The only real constraint is that the negative supply terminal needs to be at a lower potential than the positive supply terminal, generally speaking. For specific functionality, might require specific voltages, and we'll talk about that more in a little bit. And then over here, we have our output voltage. And just to be explicitly clear, this output voltage V out is measured with respect to ground. Let's quantify the parameters of our op-amp here. So let's say that we have an open loop voltage gain of 100,000 volts per volt. This is a fairly normal open loop voltage gain for most op-amp circuits. Generally speaking, you should see that the open loop voltage gain of an operational amplifier, or at least a general purpose operational amplifier, is somewhere in the ballpark of 50,000 volts per volt to 1,000,000 volts per volt. Okay. If we look at our mu A 741, we come back up here to the top. Let's see if I can find it. Yeah, it was back down there. What is it? Operating conditions, electrical characteristics. Here we go. Large signal differential voltage amplification. This quantity right here. It says that it is typically 200 volts per millivolt, meaning that its typical voltage gain is 200,000 volts per volt, but minimum is 20, meaning that you can get devices whose voltage gain is only 20,000. And since the typical or average value is 200,000 volts per volt, it stands to reason that sometimes you will get amplifiers whose voltage gain is greater than 200,000 volts per volt, right? So this 100,000 volts per volt that we're using in this particular example problem is a fairly reasonable value for an open loop voltage gain for an op amp. Our input resistance will be 1 mega ohm. Once again, this is a fairly reasonable value. Typically speaking, operational amplifiers that are based on bipolar junction transistor technology, like the MUA741, have input resistances that are measured in mega ohms. Operational amplifier circuits that are based on metal oxide semiconductor field effect transistor or MOSFET technology typically have input resistance on the order of tera ohms or 10 to the 12 ohms. So they are 1,000,000 times more resistive than a mega ohm. Okay, so 1 mega ohm is fairly standard for an off-the-shelf BJT based op amp. And then our output resistance, we will say, is 25 ohms. And once again, this is a fairly typical value for some special purpose amplifiers, particularly low noise amplifiers. This number could be as low as less than an ohm. Generally speaking, it's never going to be larger than 100 ohms. So for a good performance out of an op amp, you typically want a very, very large open loop voltage gain somewhere in the ballpark of 100,000 to 1,000,000. Your input resistance also needs to be very, very large, somewhere in the ballpark of a mega ohm. And your output resistance needs to be pretty small, somewhere in the ballpark of tens of ohms. Okay. So these are our parameters that we're going to use. Now I am going to redraw our circuit using the practical op amp model. Okay. So I'm going to start by drawing the model itself. So here's my voltage pin V plus. Here's my input resistance. So this has a value of 1 mega ohm. Here's my inverting input pin. So I'm denoting that as V minus. My open loop voltage gain is 100,000. That's the same thing as 10 to the 5. So I'm going to have 10 to the 5 times my differential voltage VD. So while I'm at it, I'm going to go ahead and label my differential voltage here. Just as a quick aside, the differential voltage is always measured with the positive polarity terminal at the non-inverting input terminal side and the negative polarity at the inverting input terminal side. Here is my output resistance. So we have our 25 ohms. And now I'm going to label my output voltage. Since we don't have a load connected, this is what my true output voltage is going to be. I'm going to extend this guy over here. There's my ground. And so I can see from my diagram that the inverting input terminal is shorted to ground. So I'm going to short this leg here down to ground. And my 1 volt source is connected between my non-inverting input terminal and ground. So I'm going to put my 1 volt source over here like so, between my non-inverting input terminal and ground. So this is how I've redrawn this particular circuit. I started with drawing the op amp itself, and then I handled all of the external connections, okay? And that's typically speaking how I'm always going to redraw these circuits. It helps me remember where things are supposed to go and all that kind of good stuff. All right, so now we're going to analyze this thing. It's not going to be particularly difficult. Our output voltage is what we are trying to find here. And by writing a Kirchhoff's voltage law equation around this loop, we can very easily see that our output voltage is going to be 10 to the 5 times whatever our differential voltage is. Well, if we write a Kirchhoff's voltage law equation around this loop, we can very easily see that our differential voltage is simply 1 volt. And from that, V out should be 10 to the 5 times 1 volt, or 100,000 volts. So does this make sense? Well, mathematically, yes, it's exactly what our circuit analysis tells us what we should have. Practically, the answer is very much no. If we went into the lab and got a simple op amp, I have probably 30 MUA 741s here in my office, and I applied 1 volt to the input pins with 10 volts at the positive supply and a negative 10 volts at the negative supply, and measured the open circuit voltage at the output, I very much would not see 100,000 volts. I'll see something much smaller. So this is what one of the limitations of our amplifier is. Notice there is nowhere to take into account the positive and negative supply voltages in our model, okay? And this is where what the problem is with this particular model, okay? So we're going to talk about this as a concept called saturation distortion. So in a real op amp, the output voltage cannot, I'm going to put a little asterisk there because we'll talk about it in a moment, exceed the power supply voltages, okay? So when the output signal is constrained to be between VCC plus and VCC minus, we call this a rail to rail op amp. Okay. Now there are certain types of op amp circuits where there is a little amount of dead space between the maximum output voltage and the positive supply voltage and the minimum output voltage and the negative supply voltage, meaning that the output can't quite get to VCC plus and it can't quite get as negative as VCC minus. For the intents and purposes of this class, we are going to act as if we're dealing with rail to rail op amps always, okay? Meaning that our output voltage will will never be more positive than VCC plus, and our output voltage will never be more negative than VCC minus. So under this constraint, what we will see is that our output voltage will have one of three values. It will saturate to VCC plus, the positive supply voltage, when the product of AVOL times our differential voltage, the nodal voltage at our input, our non-inverting input terminal minus the nodal voltage at our non-inverting input terminal, is greater than or equal to VCC plus. We call this positive saturation. On the opposite side, our output voltage will be VCC minus when AVOL times V plus minus V minus, our differential voltage, is less than or equal to VCC minus, which is negative saturation. And then in the middle, our output will be equal to AVOL times V plus minus V minus, our actual expected output voltage, when that quantity AVOL times V plus minus V minus is between VCC minus and VCC plus. And we call this the linear region of operation. So if we were to make a plot where we have the out on top and V in here, let me say this represents VCC plus and this represents VCC minus. As our input voltage changes, our plot would look something like this. Right? So our output voltage can never be more negative than VCC minus, and it can never be more positive than VCC plus. This region to the right here represents positive saturation. This region to the left here represents negative saturation. And this region in the middle is our linear region of operation, okay, graphically speaking. Now, the slope of the linear region is set effectively by the open loop gain of the system, okay? So our linear region mathematically will extend from VCC minus over the open loop gain is less than our differential voltage to VCC plus divided by our open loop gain. So for the amplifier that we've described above, where AVOL was equal to 100,000 volts per volt, VCC plus was 10 volts, and VCC minus was negative 10 volts, would actually wind up having a linear range of 100 microvolts, excuse me, plus or minus 100 microvolts, meaning it only actually amplifies the input signal when the input signal or the differential input signal is between negative 100 microvolts and positive 100 microvolts. In our next class meeting, we are going to talk about how this very small linear range is actually used for special types of op-amp circuits. All right, so that's all that I wanted to talk about for today. So unless anybody has any questions, I will see you guys on Wednesday.